Hey class, in today's lesson we're going to talk about polynomial functions of a higher degree, and that's found in section 2.2 part 1. Our objectives are going to be to use transformations to sketch graphs of polynomial functions, to use the leading coefficient test to determine the end behavior of graphs of polynomial functions, and to find and use zeros of polynomial functions to sketch their graphs. So just a little vocabulary. So it says the graph of a polynomial function is continuous. This means that the graph of a polynomial function has no breaks, holes, or gaps. It has only smooth, rounded turns, not sharp or pointed turns. So first of all, so this first one here, I'll circle in green the functions that are okay. So this function up here, A, is okay because it's continuous. The function down here, another A, is good because it's also continuous, it's smooth, it's rounded. However, B is a no-no. This, remember, is a piecewise function, so that actually won't work for us because it has gaps and holes. And this one here, B, is not also going to work because it has a sharp turn. So those are not considered continuous polynomial functions. All right, so it says graph y equals x squared, y equals x to the fourth, and x to the sixth on the same graph. What do you notice? So if we graph these all on the same function, y equals x squared will look something like that as a, parent quadratic function. X to the fourth will just be slightly inward, and so would x to the sixth, okay? And if we did the same thing for the odd functions, again, the original x cubed will look like that, and then x to the fifth, and then x to the seventh. And so what we'll notice is that the graph, the greater the value of the exponent, the skinnier the graph. So the skinnier the graph. So we're going to sketch the graph of each polynomial function. So for us to sketch, all I really want you to do is when we sketch, we just take a look in our calculator and see what we're going to get. You do want to be sure that you write or sketch specific points that you should be able to see on your function. In other words, like x and y intercepts, wherever they cross the axis, you want to specifically mark those. So anyways, if we typed in negative x to the fifth into our calculator, what we will notice is that we get a function that looks kind of similar to a cubic function, except it's negative, okay? And it goes through 0, 0. It also goes through the point -1, +1, and it also goes through the point +1, -1. Okay, so that's the negative x to the fifth function. The x to the fourth function, if we type that in, it's just x to the fourth power. And again, that looks a lot like our parabola function, except we know that +1 shifts it up 1. So it's a little thinner, but it goes through +1. So if we sketch this one, again, we can use notations or transformations from previous functions. So this +1 is actually going to move our graph to the left one, so it will kind of remind us of a parabola, except it's a little bit thinner. Okay, and it's been shifted to the left one. All right, so about this leading coefficient test. So first we're going to compare by hand, and then we're going to try and make some assumptions based off of that so that we can come up with what is the leading coefficient test. So 2x squared, if we were to graph that, it's a parabola that's been stretched by 2, okay? A negative 4x to the fourth function looks similar to a parabola function, but it's down, and we know it's down because of the way it's set up. The h of x function, which is x cubed, we know a typical cubic function, okay? But if we were to type in negative 3x to the fifth into our calculator, we get something that's a little stretched and kind of going that direction. Okay, so what do you recognize about these graphs? First of all, what we need to focus on are their endpoints, okay, or how they end. So the way that the first one ends is that this one is up and up. Look at the tails, look at the arrows of the graph. They're both up and up. This one is down and down. Our next one is down and up. And our last one is up and down. All right, so from that, you should have enough to create something of an assumption. And what I want you hopefully to see is that if you have, first of all, those two are connected because they are both even powers. So even powers are the same, or they end the same. So even powers end the same, meaning they're up, up, or down, down, okay? How do I know if it's going to be up and up? If my function is positive. So if positive, it's going to be up. But if it's negative, notice here, this was a negative 4. So if negative, it will be down. And we've had enough experience with those two types in particular that we probably could have come to that conclusion anyway. But then how do you determine the other ones? How do you know which one is going to be down and up versus up and down? Well, first of all, we know they're going to be odd powers, right? That's a 3 and that's a 5. So odd powers are opposites, meaning they give you one is up, one is down, okay? And then the way that you determine whether it's going to be down or down is based on what we think the slope would be. So this function is positive. So what does a positive slope look like? You should say that a positive slope looks like that, right? So that is from down to up, okay? If we have a negative slope, which that has a negative function, so a negative slope is just the opposite, right? We have a function that's kind of pointed downward, so that one is up to down. Okay, and that's how you are able to use the leading coefficient test. So I should be able to look at any polynomial function and determine what's going to happen to their endpoints based off of knowing if it's an even or an odd power, and then determining, once I know that it's even or odd, if the function is positive or negative. All right, so we're going to use the leading coefficient test to determine the left and right behavior. So in other words, the end behavior of the graph of each polynomial function. So first of all, you have to know what your leading power is. So our leading power is 3, so this is cubed. So it is an odd function. However, this one is odd and it is negative. So odds, remember, are opposite. So it means it's going to be up, down, or down, up. A negative slope looks like this. So the end behavior for this one is up and down. And that's it. Okay. This other one, our leading power is 4. Just because it's in the front does not mean that it has a leading power. So be sure that you're paying attention to which one is the highest power. So your highest power is 4. So 4 is even. And remember, even means that they're going to be the same. And then this one is positive. And positive means that it's up. So for us, this is going to be up and up. All right, we're going to try that again. Again, this one, the leading power is 5. So it's odd. And odd means opposites. So they're going to go in different directions. Okay. But it is positive. So a positive slope goes in the direction from down. Oh my goodness. and up. Sorry, that's supposed to be down and up. All right, so zeros of a polynomial function. So the graph of f has at most n real zeros. The function f has it at most n minus 1 relative extrema. So n would be your exponent, by the way, or your highest power. So for example, if I have a function that is x to the 5th, what I know about this, because that's 5, is that there are 5 zeros and there are n minus 1, so 4 either maxima or minima. And that's all that means. So just look at your highest power. You should have that many zeros. A little bit more vocabulary. So you have to be sure that you use the right vocabulary when you're talking about polynomials. So f is a polynomial function and a is a real number. So what they're saying is if you write it in the format x equals a, then x equals a is a zero of the function. So if I ask for a zero of a solution of a function, then the solution should look like x equals whatever that number is. If I see x equals a, that's also pretty much what I just said. It's a solution of the equation f of x equals 0, because what I did is I took the factor and set it equal to 0. So what is the factor? The factor is this next line. So if I see it written in parentheses as x minus that number, the answer would be one of those first two that are boxed in, either the 0 or the solution. For a factor, it would always be x plus or minus that number. And then the last one, where you have a comma 0, you can have a 0 like in the first one, but to write it as an intercept, you have to take that number and say comma 0. So an intercept is an ordered pair. Okay, zeros and solutions, they're just equal, and a factor uses parentheses with plus or minus. All right, so in example 3, we're going to find all the real zeros of this function, and then we're going to verify using our graphing calculator. So in order to find real zeros, what you need to do is you need to factor by setting the function equal to 0. So I have x cubed minus x squared minus 2x. Now first, what you should recognize is that the greatest common factor of these three terms is x, so I can factor out an x from all of these. And then from there, I'm going to do the AC method. So AC for that trinomial in parentheses is going to be 2. What factors of 2 give you 2? You only get 1 and 2. So that's going to give me a negative 2 and a positive 1. So 0 equals x times x plus 1 and x minus 2. Okay? And then from there, we would set each of these equal to 0. So if I set this equal to 0, that's x equals 0. Literally, we're done. If I set this one equal to 0, that'd be x plus 1 equal to 0. So I subtract 1, and I get x equals negative 1. That's my second solution. And then I take this last factor, x minus 2, and set it equal to 0. So I would add 2 to both sides, and I get x equals 2. So again, that's our last solution. So your zeros are x equals 0, negative 1, and 2. And that makes sense because this is a cubic function, and it said that I should have 3 solutions, and I do. 3 solutions / 3 zeros, same thing. In example 4, we're going to find all the real zeros, and we're also going to find the relative maxima or the relative extrema on our graphing calculator. So the first thing we're going to do is we're going to factor. So again, 0 equals negative 2x to the 4th plus 2x squared. Okay, you should recognize that you can factor out a negative 2x squared from both, and you'll be left with x squared plus 1. Excuse me, minus 1. So minus 1. And then, so you're left with, if you factor, this is difference of squares. So that would be negative 2x squared, and then x plus 1 and x minus 1. Okay, this one here, if I set negative 2x squared equal to 0, divide by negative 2, I get x squared equal to 0. And if I take the square root, technically there are two solutions, and the square root of 0 is going to be 0 and 0. So I have x equal to 0 twice. On the next slide, you'll see why. If I take this one and set it equal to 0, I would get x equal to -1. If I set this last one, x minus 1 equal to 0, I would get +1. So there are technically 4 solutions here. 0 is counted twice because of the plus or minus. I have a -1, I have a +1. It is okay to duplicate or have more than one 0, okay? Then the last thing that we're going to do is we're going to find the relative extrema. So remember, we typed this into our calculator, so that's -2x to the 4th plus 2x squared. If we graph that, what I see are two relative maxima. If I sketch the graph, it kind of looks like, let me zoom in a little bit. That'll be, I'm going to change my window to -5, +5. And so what I see is a kind of like a graph that makes like a little M shape. And so essentially we're looking for these 2 points on top, okay? So I would do second trace. These are both maxima. So scroll to the left, scroll to the right. Our first maximum is, or relative maximum is what I should say. The first one, remember these are ordered pairs, so it's -0.71, comma 0.5. Okay. The second one, I would do second trace. Again, that's a maxima. And I'm going to do left bound, right bound, and enter. And this relative max is +0.71, comma 0.5. And that's if I'm rounding to the nearest tenth. And we're done. Okay, so as I was explaining the last one, so it says in example 4, the real 0, x equals 0 from -2x squared equals 0 is a repeated 0. So in general, the factor of x minus a to the k yields repeated zeros of x. Sorry, I don't actually know what that was supposed to say. I think it's a little off. It should have said of zeros x equal to a. Sorry. Of multiplicity k. If k is odd, the graph crossed the x-axis at that 0, meaning it's a chest pass. So, you know, if you're playing basketball, you do a chest pass. That means you pass the ball straight from your chest to the next person's chest. If k is even, then the graph touches the x-axis at that value. So it makes a bounce pass. Like that means take the basketball, bounce it to the ground before you bounce it to the next person. Alrighty. And specifically a chest pass, what that would look like. Each of these are chest passes. They go through the x-axis, but a bounce pass means that it bounces up. This would be an example of a bounce pass because it bounces at the x-axis, and this one is an example of a chest pass because it goes through the x-axis. Okay, so again, this one was squared. So what that means for me is because it is even, that means it's going to be a bounce pass, so it's going to bounce back up, okay? Anything that is odd goes straight through the value. Okay, so we're going to find all the zeros once again, and this time we're only going to use the graphing calculator. So to find all the real zeros, your steps are, first of all, you need to type this into your calculator. So we would have x to the 5th minus 3x cubed minus x squared minus 4x and then minus 1. Once you graph it, you will get a graph, and mine is kind of not showing so well because I'm a little zoomed in. So I'm going to change it to a standard window. So -10, +10. And -10, +10 doesn't work either. So I'm going to change it again to -15, +15. The reason I'm doing this is because I'm not seeing my maximums. Now, technically, I don't really need to see them because we are looking for the zeros. And remember, that's where it crosses the x-axis. But anyways, if we were to sketch it, mine now looks something like that. Okay, so we're trying to find this value, and this value. Okay, now in order to do that, you have to do left bound, right bound with your calculator. So you would press second trace and go down to 2, which says 0. Now, to do these, you always start from the left and kind of turn your head. So this is actually left bound, and this will be right bound for the first point. If I keep going around, now this is left bound and right bound for this point. If I keep going around, turning my head, this is now left bound, and this will be right bound for that last point. Okay, so to find our first point here, left bound is below the x-axis. Right bound would be right above. So that value as a 0 is x is about negative 2.07. Okay. The next one, if I do second trace, 0. Okay. Left bound, again, should be just right above the x-axis. Right bound is right below. So that value is about negative 0.16. Okay, and then our next one, or our last one, so I'm now talking about this one. I do second trace and 0. Your left bound is below the x-axis, right bound is above, and that value would be about 2.11. Okay. And that's how you would find it on a graphing calculator. All right, class, so we're done. So if you have any questions, please come see me for tutoring.